All right, can you guys hear me okay? If somebody could say something to let me know sounds good. Anyone? Audio? Can you guys hear me okay? Okay, you're typing in the chat box instead of verbally. Okay, I got you. All right, cool. All right, we're gonna roll then. All right, welcome. I got you guys for about the next hour or so. Our goal today is to go through indoor air quality stuff, specifically some of the problems that are in homes and even buildings, and some of the various solutions in our industry that can solve some of that stuff. This is not product specific per se, although some of the solutions will be products that we in fact are aware of and that we utilize. But it's more just general knowledge, just like many of the stuff in this particular training series we've been doing. So ask me questions as we go. I'll try to check that chat box periodically, but if not, if you can just unmute yourself and ask, then I'll obviously get my attention captured that way. So here's kind of the stuff that we're going to cover through. We're going to go through different kinds of pollutants, filtration, and then air purification technologies to solve that stuff. So if you didn't know, there are three major categories of pollutants of stuff floating around in the air. There's particulates, microbials, and gases. Particulates are essentially chunks of debris, like physically large enough things that you can see or almost see. They can be small enough that you can't see them, but just stuff floating around the air. So it could be dust, it could be pollen, that kind of stuff. The three biggest categories of particulates are dust, dander, and pollen. Uh, Pollen obviously comes off of plants, dander comes off of your pets, and dust, sadly, a large portion of that comes off of human skin cells. There could be other stuff floating in the air as well. But these things are all out in the air. You're essentially breathing them in constantly inside your house or inside the buildings that you visit. They're coming into your lungs. Your lungs are filtering them. That would not be the ideal place to filter stuff. We'd much rather filter it mechanically and not have your breathing system be the main filtration option. The second category of stuff in the air is microbials. These are essentially living organisms. Generally speaking, they are harmful. There are ones that are not, but most of them are, at least the ones we care about today. So those also have three major categories: bacteria, viruses, and fungus. Bacteria, obviously, there's good bacteria like in your stomach, breaking food down and stuff. But we're mainly concerned with the bad bacteria that's in the air or on counters or stuff like that. So stuff that gets you sick. So, for example, strep throat is caused by a bacteria, a staph infection, E. coli on chicken, that kind of stuff. Then there's viruses. Viruses are technically not living, but I count them as living. I'll say things like, let's kill the viruses, right? But they're not really alive, so you can't kill them because they need a host to survive. So they are sponging off of you in order to even have basic function. But they also cause various illnesses, right? The one you hear in the news right now is avian bird flu. That's a virus, right? Um, SARS and any SARS derivative like SARS-CoV-2 causing COVID-19, virus. Influenza, right? The flu, if you will, virus. Common cold, virus. Norovirus, obviously a virus. And then we have fungus related stuff, mold stuff. There is also good and bad mold. For example, the kind of mold that penicillin is created from can be very beneficial. People need penicillin for health reasons, right, to solve various problems. So there is mold that is good. But in general, mold in our building, not good, right? So something that growing behind your drywall or whatever in your basement, not good. Um, this is my house. This is where I live. I actually grow mold on purpose. It's enjoyable. I like to see it flourish. Obviously, it's not. I just Googled a random picture, and this is the grossest thing that came up in the first 10 views on Google. So I'm like, all right, that's the one we're going to roll with. This is obviously a house, and it's obviously very badly have mold infested. The whole ceiling is absolutely covered, and you can, I don't know if you guys can see, but like there's actually like mold on the wall, almost like in a flowing pattern, the way it kind of curves down. I don't know what was happening in this building. It was just a random Google picture. But I'm guessing something up above this ceiling, probably the roof, was badly leaking, water everywhere. And this wall right here is the place it found its way downward with gravity. So obviously from the backside, the whole ceiling gets messed up, and then wherever it can drain down gets messed up. In order to grow mold, you need to have three different things. You need to have mold spores in the air. they're everywhere. Like there's millions of them right in front of my face right now. So they're everywhere. You need to have a food source, and that could be anything organic. It could be, bread on, on your counter. It could be the orange I talked about with penicillin, or it could be drywall, paper in the drywall, pressed wood of your desks, right? Dirt in the bottom of your mat, in the walkway into your house. Like anything that was ever alive, it can eat. So that's hard to get rid of as well. And the third thing mold needs is moisture, it needs water. So water is the one we usually try to get rid of. It's hard to get rid of the mold spores. It's very hard to get rid of everything organic, everything that was alive in your house. It's much easier to control the water. Obviously, a roof leak is not an HVAC problem. A pipe leak, probably not an HVAC problem unless it's off of a boiler. If the moisture is being held in the air, then it does become an HVAC problem. It is our fault that it is there, and we got to do stuff to dehumidify the air to get rid of it. These things, no matter what they are, viruses, bacteria, mold, fungus, they all reproduce pretty quickly. So if things start getting out of check, it gets out of check quicker and quicker and quicker. So we want to do stuff to continuously eradicate and remove these things, as opposed to letting them build up to a large quantity and then trying to get rid of them. The third category of stuff for indoor air quality in your buildings and homes is gases. That's all kinds of different stuff as well. It could be fumes from people storing paint in their basement, right? That would be gases in the air. It could be volatile organic compounds from the glues and adhesives used to manufacture, chairs or something or whatever they have in their house. It could be the paint they painted their wall with. It's probably not low VOC paint. So the two major categories of gases are VOCs, volatile organic compounds. These are things that people generally find to be irritating, and like medically irritating, that cause actual physical problems, like with throat irritation, nasal problems, etc. Then there's odors. Odors, generally speaking, are not harmful to you, but they're just things you don't want to smell. Like, I don't really need to smell my kid going to the bathroom, right? Dude, turn the bath fan on, let the air get sucked out of there, right? So odors are things that we are not harmed by, but we don't want to deal with it, right? Maybe you live in an apartment building and every Wednesday your neighbor cooks some weird food that you don't like and you smell it in the hallway, right? That's annoying, but you're not gonna get sick because this person cooked a weird smelling food. They decided to cook fish every Wednesday or whatever they do. Most homes, well, it doesn't matter whether they're new or old, by the way. The statistics are basically the same. Most homes have indoor air quality problems, at least one. And many of them, as you can see here, almost 80% of them have at least two problems wrong in their house, or more. It gets worse from there. These are the most common problems that we generally have in residential homes for indoor air quality. Um, Carbon monoxide, we do a really good job of solving that. If there's carbon monoxide in people's houses, they generally die, especially if it gets above a certain quantity. So we've become really good as an industry, both HVAC and fire departments and general awareness, um, marketing ads even on controlling carbon monoxide so people don't get sick in their home and die. All right, so that one we're good at. We're pretty good at controlling temperature. I mean, not great. As you can see here, 79% of the people are happy, but means 21% are not happy with the temperature of their home. So we could do a better job with that. We have the equipment to do it, but for some reason, we're not always doing it the right way. Or we'll do a good job of getting the right temperature in the room that has the thermostat, the dining room that no one uses, but then the bedroom will be freezing, right? So we're not good at making all the rooms equally comfortable. But overall, we're good at temperature. We can do a lot better job with humidity. We're pretty good with humidity in the winter. Our industry, we install humidifiers to add moisture to the air in the winter. We do a really bad job at dehumidifying in the winter. We could do a lot better with that. And it's not because we don't have the technology, it's because we're not offering it to people in the right way, or we're doing it wrong as an industry. A lot of times it's just a function of how you've sized the AC equipment, and that's enough to dehumidify correctly if you stop oversizing it. Carbon dioxide is not a pollutant, but we do use it as a measurement for how much ventilation air we have in the building. We use it as a surrogate. So we could do better there too by bringing more fresh air into buildings. VOCs, as I mentioned earlier, in particulate matter, we've done a really poor job as an HVAC industry on keeping that stuff in check. When people are polled and asked what they'd like to do to improve the indoor air quality, and by the way, this is pre-COVID, this screenshot. So maybe the answer would be different now with people's awareness of viruses. But generally speaking, historically, the number one answer on what they would approve is dust. Dust isn't even harmful. Like it's not desirable. I don't want my house to be dusty, but it's not doing me any harm. In fact, I said most of it's skin cells coming off my own body. But people always reference that one because that's the visual one. That's the one you can actually see. I can't see the bacteria. I can't see the mold behind the wall, so I don't know that's happening. But the dust, I see it, so I know it's happening. So the visual stuff people ask to resolve more frequently than the invisible stuff. But generally, the invisible stuff is more important to get rid of. Um, People put a lot of portable stuff in their buildings. They go to Walgreens and they buy a humidifier, right? Or they get a dehumidifier at Home Depot and plug it in their basement, right? Or even portable tabletop air purifiers that were super popular, during COVID and any other virus scare. By the way, every couple of years we get some kind of virus scare. I think we're back around again to avian bird flu is back up. It's been a while since we've had that one, so now we're back on that. I know we had, SARS-CoV-2 recently, right? COVID. That wasn't the first time we've had SARS virus breakouts. So this stuff just goes around in circles. Whatever we can get scared of recently. In any case, if people have portable stuff to solve problems, pretty good chance that they need permanent things to be installed. They just don't know how to do that, or they don't know who does that, or they think it's going to be too freaky expensive to do that, right? But if you're sitting there hand filling 6 portable humidifiers, one in every room of your house every morning, you might as well just get a humidifier and mount it on your duct and let it automatically do it. All right, solutions for that kind of stuff. The number one solution we have available to us is filtration. Absolutely no one is going to push back on filtration. No one's going to say, oh, filtering the air doesn't clean the air, right? Everyone believes it cleans the air. There's various levels of filtration that we can have doing better or worse jobs of cleaning the air. So in order to understand how a filter works, we kind of have to understand how big the stuff we're trying to catch is. So this scale here is in microns from something very small to something very large. The large thing on this scale is sand, which is obviously pretty small. Like I could barely see 1 grain of sand, right? On the far left side is the really small stuff like gases. I'm not able to see oxygen in the air, right? I'm not able to see nitrogen in the air. Also, don't want to get rid of oxygen and nitrogen, but the really small stuff. So big stuff like sand, hair, pollen, I can catch that pretty easy with mediocre filters. If I want to catch small stuff like smaller bacteria, viruses, odors, I'm gonna have to do something different than the normal situation. Another way to visually look at that on the left is 1 grain of sand as compared to the width of one human hair. I don't know anything about that, but I hear that hair exists and there's a width to it. And then this little blue thing right here is a PM10, particulate matter 10, and the red one is particulate matter 2.5. 10 and 2.5 microns are the two de facto sizes of things that we measure when we're determining how good of a air cleaning system we have. The whole industry just measures PM10 and PM2.5. I don't know why, it just kind of evolved that way. It is what it is. By the way, this little tiny dot right there in that little box, that is a SARS-CoV-2 singular virus at 0.12 nanometers, micrometers, excuse me. One last way to look at that, on the right in the black circle is a PM10. PM2.5 is the little black circle. One single red blood cell from your body is this guy right here. Here's an example of one bacteria. And this is not a virus. This little dot down over here is a virus. Specifically, that one's a SARS-CoV-2 virus, which obviously was the COVID causing one. And when I put that over on my chart over here, it's one of the bigger viruses we've ever had to deal with. It's super easy to use good filtration to catch COVID virus. Um, and this is not like this is new information. We had this information the day that the COVID stuff started. We already knew all of this. People didn't use the right solutions, but nonetheless, it's easy to catch and eliminate COVID virus. It's easy to kill it as well. And we'll talk about that later. We just didn't do a good job as an industry making sure people had those tools. Some of us did. Like, I have any problems at my house, but other people did not. From a filtration standpoint, there are 3 technologies we use to catch stuff. We're going to skip chemical because that's for like industrial processes, so we don't need that. So mechanical and electrical are our 2 major ways. The electronic filters are out of favor. There's one shown down here from Honeywell. Most people do not utilize those anymore. They work fairly well. You can catch small stuff with them. The problem is they need to be periodically cleaned, like basically every month. And generally speaking, Americans are lazy and we do not want to clean and wash a filter and then put it back in, especially not 10, 12 times a year. So we've all reverted back to what we've always done in the past, which is disposable filters that we throw out. So you can still get electronic air cleaners. Um, those exist still, but they're not popular, and pretty much everybody's using mechanical filtration. Mechanical filters have four ways of catching stuff: impingement, interception, straining, and diffusion. On each of these next four drawings, this blue circle right here is one fiber of my filter. So if I had a fiber glass filter, which is a normal type of filter, it's one little pin of glass, if you will. If I had one of those green or blue, like plastic woven filters, it's one little piece, one little string, if you will. So this is something that's super tiny and probably about the same width as your hair, right? From left to right is the air moving through the filter. So I'd have a whole bunch of filter material here. This little orange, purple, red, whatever color that is one piece of dust in the air. So impingement, that's when the debris in the air collides straight into the fiber of the filter, like as a head-on collision, just drives his car right into the brick wall, boom, stops, that's it, he's done. That's impingement. Interception is it did not have a head-on collision. It had a glancing blow, like it almost made it around. But when it went around the fiber, the friction between the two slowed it down. Kind of like if you were getting onto the expressway and you're getting onto the on-ramp and you're not paying attention and your car's grinding along the side rail, like you looked at your phone or whatever flaky thing you did, it's grinding on the side rail. That would slow your car down because of the friction between your car and the side rail. So the debris comes in, it has a glancing blow, the friction slows it down until it comes to a halt. That is called interception. There's like an attraction force called van der Waals force that clings those two things to each other. Straining is the easy one. This is like totally the most mentally logical one. I have two pieces of fiber near each other. There's a small gap between them. The piece of debris is fatter than the gap. It's not going to fit through. So this is a pot of spaghetti. You pour it through the strainer. The water is small. It fits through the holes. The spaghetti is fat. It does not fit through the holes, and hence it gets stuck in the strainer. It's the exact same idea right here. The gap is small and it can't fit through. By the way, once that happens, the next piece of debris coming down the pipe has even less places to fit through because this dude's plugging up one of the holes. So the dirtier your filter gets, the better your filter is at filtering. I know that sounds kind of weird because we're always like, oh, change your filter. Dirty filters filter the most stuff. The problem is when they get too dirty, they actually block the air as well. Well, we can't have the airflow blocked because then what the hell are we doing? I mean, I could put a brick in your duct and it will stop a bunch of airflow, but I can't move air through the brick and hence I can't heat your house. So the dirtier the filter is, the better it is at filtering, but the worse it is at airflow. So we're always trying to change filters kind of at that point where it's like, okay, I did a really good job filtering, but the airflow is getting a little bit low. Time to change the filter. That would be the ideal scenario. The fourth and final way is the weird one. And I always want to skip this one because it's hard to explain, but we need it later on when we talk about something else. So we need this back end knowledge. So same drawing, same filter, same fiber, airflow's moving through it, but now it's not a piece of dust. It's something significantly smaller than dust. In this case, it's a little tiny virus. And you notice the virus did not have a straight pathway. He's got this zigzag pathway. That's because really small things do not give a crap about airflow or gravity. Really small stuff doesn't care. So gravity, I'm assuming you're all familiar with that, right? If not, stand up and lean to the side really far. You'll figure it out. Gravity is the attraction between two things. Most of the time, we're thinking about it in terms of the earth as one of the two things. Like I drop this water bottle, boom, right? Gravity pulls it down, right? My body, I trip and fall, gravity pulls me down. But there's a gravitational force between everything in the universe. Every single thing is pulling on everything. Right now, this phone and this water bottle are pulling towards each other. It's almost immeasurable because the earth is so much larger and so much more massive than these two things. The earth is pulling them down more than they're pulling at each other. So once we're near the earth, which we almost always are, gravity pretty much gets associated with earth only. But it is very much a function of how close things are to each other and how much mass they have, how much they weigh. So a virus, as you'd imagine, doesn't weigh very much. It's super light. So it can float around suspended in the air and gravity does not pull it down. If it did, all the viruses would land on the floor and I'd just vacuum them up every day and that'd be that. And then we'd solve the whole problem, right? But they don't. They just float around in the air doing whatever the hell they want. Just like carbon monoxide floats around in the air and humidity and all kinds of other stuff that are light enough that gravity doesn't do anything to them really. So this virus is floating around in the air doing its thing. It also does not really care about airflow at all. So if you can imagine a ship with a sail on it, The wind blows the sail and the ship goes sailing along really fast. When you put the sail down and it's just the mast, and this is the only way I can describe this, it's just the mast, pushing on that little tiny surface area of the mast doesn't move the ship very fast. Put the sail up and it's going, but the sail's down and it's just pushing on the mast and maybe the back of the boat. Nothing's really happening. So the same thing happens with the virus. It's so tiny that it doesn't have any surface area, so airflow, i.e., wind, doesn't really affect it much. Like it just does its own thing. It does move around the space a lot, but it doesn't move around because of gravity pulling it down or airflow sucking it or blowing it one way or the other. It moves around by bouncing off other crap. So there's all kinds of tiny crap in the air, and all that crap is moving around and bouncing off each other. And every time they collide into each other, they go scattering in different directions. They collide into somebody else and somebody else and somebody else. That's the zigzag pattern. It's all over the place. So even if you put in a really awesome filter that can catch viruses, the chance of the virus getting to the filter is fairly low. I cough, it comes out of my mouth. I'm I'm 30 feet away from the return duct. Even if I cough my face right into the return duct, it's going to bounce around the return duct for a while. It may or may not ever make it back to the actual filter. So using a filter to catch really, really tiny stuff is hard. We can catch big stuff that way, pollen, dust, right? That kind of stuff. But viruses and gases, catching them with a filter, it's not impossible. It's just really hard. And that's going to come into play as we talk about more stuff. Anybody have any questions as we're going through stuff here? Type them in the chat box and I'll do my best job to answer them. Or the question box. I don't know which box I enabled. I don't really know why there's two of them to begin with. All right, I'm going to keep talking. And if you guys have something, type it in or unmute yourself and just go ahead and ask it. That's totally fine as well. All right, so we have these filters, and there's a rating system for filters that indicates how efficient the filters are. So the scale goes from 1 to 16, and we call it the MERV rating scale, minimum efficiency reporting value. Not that you care what it means. It goes from 1 to 16. I realize my chart also has 17 to 20. 17 to 20 is not part of the actual scale. That's something that we added on here to kind of try to represent where a HEPA filter would be if a HEPA filter was in fact MERV rated, which it is not. So 1 through 16 is a normal filter scale. HEPA is in its own system, its own category, if you will. The smaller the MERV number, the crappier the filter. MERV 16 would be the best non-HEPA filter that you could have, and a 1 would basically be, dude, it'd actually be worse than the shirt. The shirt's probably a MERV 3, right? It would be really bad. So it's basically nothingness, right? Most of the filters that we use in our industry are like around a MERV 8. That's like a pretty normal average filter. You can go to Home Depot and get a really crappy filter that's like a MERV 6. I don't know why you're doing that, but you can in fact do that. We can upgrade filters and do MERV 11, MERV 13. Those are pretty common ones. And once we want to get above MERV 13, it becomes challenging because above MERV 13 tends to restrict the airflow unless we use certain kinds of technologies to get above 13 in a special kind of way, which I'll explain. So, and this tells you the kind of size of stuff that it catches. So if I had a MERV 12 filter, let's say I'm catching between 1 and 3 micron stuff. Let's just say it's on the good end. It's a 1 micron size stuff for that MERV 12 filter, right? So 1 micron is right here, this line right here. So yeah, I'm catching sand and hair and pollen and stuff like that. I'm doing a good job of that. I'm not really doing anything for odors and viruses and gases in this space. I'd have to do pretty good. Just to get some of the odors and some of the viruses, I got to get down to a 0.01, which means I got to be down into the HEPA filtration range typically. If I get a MERV 13 through 16 filter, maybe 0.1. So I'm right here on this line. So I'm catching pretty much all the bacteria at that point, most of the dust, right? But it's hard. So when you get to a higher MERV rate filter, a lot of times they get more restrictive. Specifically, the one that comes up a lot is like the 3M Filtrate filters. Like all the techs like to make fun of that one because every time you go to a house and they have an airflow restriction, it seems to be like they have that filter. The filter is really good at catching small stuff, but it's super restrictive, and that's how it catches small stuff. It just blocks the whole pathway up. People buy it, homeowners buy it. They walk into Home Depot, they're carrying whatever filter they have in their hand. It says, 20 by 16 by 1 on the side. They go to the section of the aisle, it says 20 by 16 by 1. And there's cheap ones down at the bottom and decent ones up top. And then right in the middle is like the high-end allergen, save your kid's life kind of filter. And it happens to say 20 by 16 by 1. They grab that thing. They put it in, and it's good for a few weeks. And then it's full of stuff because it did a good job catching it. And now I don't move enough airflow. That's always been the historical problem. The other way to catch a lot of stuff is to not have a 1 inch filter. Do something different. Here's the different things that we can do. In this case, it is in fact a 1 inch filter. Actually, that could be a 2 inch. I can't see. Let's pretend it's a 1 inch filter. In an air handler or even in certain large rooftops, we put the filter in a V-bank fashion. So we put the filters in like this. And if you didn't know, CFM is cubic feet per minute, and area is square feet. So if I divide cubic feet per minute by square feet, I get feet per minute velocity. So what ends up happening is if I have this duct and I go to a wider space in my duct, I'm making it wider, and I could choke it back down later, right? So let's say I'm moving, I don't know, I'm moving a certain amount of CFM. Let's just say for argument's sake, I'm moving 1,000 CFM of air. And let's say I'm doing it at a velocity of 1,300 feet per minute. When it goes to this wider open space right here, this area right this way, it's still the same air molecules moving through. It's still the same 1,000 CFM of air. And when it leaves, it's still the 1,000 CFM of air. It's always the same volume, unless I have leaks or something, then that's different. But the 1,300 feet per minute, the velocity, when I go to the wider section, it slows down. Let's say it slows down to 500 feet per minute because it's a bigger area. And then when I go back down to the smaller, it's back up to 13 or whatever size duct I put in. So if I make the area wider, I can slow the airflow down. And it's significantly easier to catch stuff in the air when it's going slowly. When it's going fast, the velocity pressure just shoves it right through the filter. So I want the airflow to go slower. So ideally, when the airflow comes into your furnace or your rooftop or whatever it is, I'd like the size of the duct to like triple. If I get a triple large duct all of a sudden, it would slow everything down and that would be great. Well, if you imagine the furnace in your basement, if the return duct was 3 times bigger than it is now, like what the heck, dude? Like where am I supposed to fit this stuff? It really wouldn't work very well. So we don't do that. We don't do it on residential. We don't do it on commercial either. We can't afford that kind of space. But what we can do is put these filters in this V-bank. So you can imagine if I just had the same exact dimension filters and I stacked them, I would have like one here and I'd have one here and that would be it. But now instead I get 1, 2, 3, 4 by putting them in a V-bank fashion. So which gives me more surface area. And the more area that I have, the slower the velocity is going to be. So as the air moves through that V-bank section, it temporarily, just for that half a second, slows down. And it slows down enough I can catch stuff on the filter better than if I did not do that. We don't do this residentially either because then I would need filter racks that are like 3 feet wide, which no one wants to do either. So residentially, we use pleated filters, right? Pleated filters means there's all these little folds in the filter, right? So if I cut this filter apart, or I didn't cut this apart, somebody else cut it apart. It's a 20 by 20 by 5. They cut the cardboard out and then stretch the filter material, and it's really actually a 20 by 13 by 1/10 or whatever, right? So that's 13 feet from there to there, and then it's 20 inches this way. It's a giant surface area, so it slows the air down pretty good. And this one happened to be only a MERV 8 filter. So it's like a regular decent filter, right? Um, if you look at some of like the really high-end filters, like one of our Infinity or Evolution filters, I showed this picture to guys in class. I got this off the internet from a post that someone made. I showed it to guys in class, and they were like, "Oh, it's cut apart one of the Infinity filters." I'm like, "Dude, that's like an $80 filter. We're not cutting it apart." So then we went ahead and cut it apart when I realized it wasn't my money. All right, so don't tell Skip. But we cut this thing apart, right? It was a 24 by 20 was the one that I cut apart. This is our actual lab in Melrose Park, and we measured it out. It was 42 feet all the way down to the end. It's a lot of surface area. These pleats are like tight. They're dense. There's a lot of material in there. Lots of places to catch crap and a lot of surface area to catch it on. So to get better filtering, you need to have filters that are thicker. So this dimension here can't be 1 inch. It needs to be something bigger than that. I'll do it this way. It can't be 1 inch. Like this one is probably, this one's 5 inches, right? It's got to be 3, 4, 5 inches from end to end. 1 inch isn't going to get it done. Either you're not going to have enough material or you're going to have so much material, it's a filtrate filter and you can't move any damn air through it. So more material folded up and in a deeper length is the way to go. So the real low end filters, you've all seen these. We have some of these ones. They're like MERV 6s, if that. They're only really good for two things. They're good for construction, right? So someone's putting together a house or whatever. There's all kinds of drywall dust and crap. You don't want to put this filter in it $80 cost to our contractor, and who knows what it is to the homeowner. I want to put this cheap filter in, and I'm just change it every week. Just throw all the drywall dust out and put a new one in constantly until the place is actually ready to go, right? That's the one time it's good. The other time it's good is as a pre-filter. Like you're going to buy two filters and run air through both of them, right? So I might run this filter, but I don't want this filter to get wasted catching big crap. So I let this guy catch the big crap. The small stuff makes its way through, and this guy catches the small stuff. So like at my house, I have this filter, and then I have one of these filters on the outside air intake, basically just catching pollen and cottonwood and big crap. So you could do that as well. Beyond those simple filters, the kind of stuff that we normally use, we use a lot of MERV 8 filters. If we're talking about like our Carrier Bryant stuff, we use a lot of MERV 8 cartridge ones, and we use even more, at least I think we still do, of the Easy Flex ones. Those are the ones that collapse down, and they put the little end caps on them. People like those because when they're collapsed down, they fit on the truck, right? So, for example, here's one of those Easy Flex filters, but when it's in the cardboard box, it's only that big, right? And the technician extends it and puts the caps on to keep it big. So it fits better in the truck, so people like that. MERV 10 far outpaces our MERV 13 sales. I don't know what the ratio is, but I bet it's like 98% of them go MERV 10 and none of them go MERV 13. But the price difference between the two is super small. It's like to go from a MERV 10 to a MERV 13. I mean, it's like $6 to the contractor or something like that. It's really low. I might be wrong. Maybe it's four, maybe it's eight, but like it's basically $6. So there's no reason not to do it. MERV 13 is way better filtration. And the grand scheme of a service contract for a homeowner, $6, even if they double the price and it's $12 more, you're already charging them 100 plus bucks to do it. What's the difference? Like charge them a little bit more and give them really awesome filtration. So that would be an easy upgrade for people that have existing systems. As you might guess, we also have all the other brands. We have all the Honeywell stuff. We have April Air. We even have Respicare filters, although we don't use a ton of them, right? But we have those other brands. April Air and Honeywell are the big names, so people know those. And obviously we do Carrier and Bryant because that's what we do everything of, right? Beyond that kind of stuff, we have HEPA filters as well. HEPA filters, as I said, are not on the MERV rating scale. They do a really, really, really good job of catching everything, but they are horrific for trying to put air through them. In fact, you cannot put air through them for a regular residential house. It's too restrictive. A regular furnace is operating at like zero point 0.5 inches of static pressure. These things have like 1.5 inches of pressure penalty. Well, if I only have zero point 0.5 to begin with, I can't use something that has 1.5 that it needs. We use these in hospitals all the time, right? Surgery suites and stuff like that. They just put bigger fans in and use more energy to shove the air through. But it's a hospital. They're not concerned about energy. They're concerned about somebody getting an infection. Residentially, if you want to use one, you can. We sell them. I recommend you don't use them. But if this is my furnace with my duct coming off of it, F for furnace, S for supply duct, it's an S. And here's my return duct coming down. What you have to do is you actually have to pull, you can't just put it on here like a normal filter. What you have to do is pull air off of it, run that air through a separate box, and then dump that air back in. And that separate box has to have 120-volt power to it. It has its own fan system inside it. And then it has this HEPA filter media that's super thick and dense. But it can only do like, say, 25% of the total airflow. So your air is coming down the duct, 75% of it doesn't go into the HEPA filter. It just goes right back to the furnace. And maybe 25% gets sucked over into this filter. So you still have to have the regular filter too. But only 25% goes to the HEPA. So my argument is like, well, that means 75% doesn't get the special filtering. So like there's still a lot of germs in the air. And if I was a HEPA filter salesman, which I am not, in fact, I'm not a salesman for anything. I'm kind of the anti-sales guy sometimes. Everyone yells at me for talking people out of stuff. But if I was the guy selling up a filter, like, well, Ryan, the air is just gonna go around to the house, it's gonna come back through, and we'll get it next time. I'm like, well, you get 25% of it next time, 75% miss still. And they're like, yeah, Ryan, I got yeah, true. But like if it goes around like 6, 8, 10, 38 times, I'll eventually get it. I'm like, dude, do you have any idea how hard it is to get a virus to get sucked into the return duct when it doesn't care about airflow? Like, good luck. If you get it there twice, you're doing really good. You're not gonna get it there 38 times. So it's kind of a stupid idea. I would not put in a HEPA residentially. Hospital, or to put a big fan in with it, no problem. Don't care about my electric bill, no problem. But regular residential, there's 50 better ways to do it. These are some of the better ways to do it. Obviously, the Carrier and Bryant one are the same. So it's really just three ways that I'm showing you here. One is the Infinity or Evolution Air Purifier. I'll explain that briefly. We have Secure Air, which is kind of an upgrade to the Infinity Evolution Air Purifier. And then we have Respiracare Ultra Clean 99, which is kind of a alternate path for people that don't do carrier and brand stuff, like one of our Heil dealers or something like that, right? It's another option. So essentially what's happening with all of these is they're using more than just the filter. They're using a filter plus electricity to get it done. So it's like an electronic air cleaner, but it also has a disposable filter media because once again, we're Americans and we're going to throw stuff out. We don't want to clean anything. So it's kind of combining those two things into one. So inside the filter media for the Evolution Air Purifier or Infinity, there is a there's a metallic material woven into the fibers, and there's literally contact points on the actual filter, right? So when you take this door off, there's little metal contacts on there, positive and negative, and we literally run power through the filter. Specifically, we run 18,000 volts. Normal stuff in your house is 120. This is 18,000. Now it's 18,000 super low amperage, but nonetheless, it's 18,000 volts. And 18,000 volts will in fact electrocute most things, right? If I stick my hand in there, it's going to be a bad day. I'm not going to die because it's low amperage, right? But my skin cells are going to die where I grabbed onto the wiring. If I'm a single cell organism, I only have one cell. As soon as it gets electrocuted, my life is over. That's it. I'm done. So viruses and bacteria and stuff, it's like one shot at life, and then that's it. They're dead, right? And then their buddy touches it, and he's dead. Whereas if I grab it with my hand, I have billions of cells in my body. I've lost all the ones on the surface of my hand, but there's new ones right behind those ready to go. Still sucks though, right? So it's killing germs by basically electrocuting them to death. It's doing that. It is also capturing more of them than normal because as the air comes through, it is ionizing it, or rather, it's charging it. So, for example, it charges all the air coming through negatively. And on the other end, the filter, if you will, is charged positively. And negatives and positives attract to each other, opposites attract, and they cling on to each other. So the filter is holding stuff onto it via electrostatic just like an electronic air cleaner would have done, except now I'm doing it on a disposable piece of material instead of a plate that I have to wash by hand, which no one wants to do anymore. So these filters will catch high amounts of stuff and they'll kill stuff. Specifically, they're certified to kill influenza, which obviously is the flu. Where'd my little mouse go? Influenza, common cold, strep throat, and then a couple years ago, they got them certified to show that they would kill the coronavirus, right? Which obviously was a big deal at the moment. So it kills all that stuff, and I'm sure it kills other stuff too. They just don't pay 100 grand to test every single possible virus or bacteria. But all the ones that we've tested are the common things, and it does a good job with those. Questions on those? Because these filters are deeper than a regular filter, they're not 1 inch, they're like 3.5 inches. And because they're using electricity, the internal material doesn't have to be quite as dense. And it can still capture stuff because of electrostatic power. So by not being quite as dense, airflow can still go through it fairly well. So these are high MERV, specifically to MERV 15, high MERV filters that don't have a lot of pressure drop penalty. Whereas if I got one of those, 1 or 2 inch filtrates, it would be high MERV. It'd do a really good job, MERV 14, MERV 13, something like that. But it would have a big pressure drop penalty, which causes high limit trips and other problems with the furnace. So that's what these are really designed to do. Capture all this crap, but do it in a very efficient way that doesn't reduce the airflow. Specifically, they call it capture and kills, like little nickname for it. Secure air, which we've had, dude, I don't even know. Maybe like commercially, we probably had it pushing, we'll just say 15 to 20 years for commercial hospitals and stuff. We've been doing this. And then residentially, the year before COVID, we started doing this. Well, they started doing residential, and we also did it with them. They designed it and built it, obviously, and we started selling them. Um, it's also really good at capturing small stuff. It also uses both a disposable filter and electricity to tag team that responsibility. It does work a little bit differently. Instead of charging everything, say negative, and then the filter is positive, and hence it clings onto the filter. In this case, air going through the filter, the filter mechanism charges some of the stuff negative in the air and charges other stuff in the air positive, and then those things cling onto each other. And once they cling down to each other, instead of six small things, they're one large clump of something. And the large clump is more likely to get stuck in the filter because it is, in fact, a large clump. If it doesn't get there and it charges the particles and they make their way through and don't get caught by the filter, they then go out into the space, but now they have a charge on them. And other stuff in the space has a charge on it. And those things clump together, and either they clump together that they're heavy enough that they fall to the floor and get vacuumed up, or they're big enough that they get caught in the airflow finally and get sucked back to the filter on the next time through. These are a little bit more expensive than the carrier ones. So the dealers we have that are using these are typically doing like a how do you do it? Like a good, better, best sales strategy. Like, okay, the good filter is a MERV 13, better is an Infinity Evolution, and then the best is the Secure Air or whatever. And some people want the best, so they buy that. Other people are like, I don't want to pay for the best. It's super expensive. But I also don't want to do the low end thing. That doesn't sound great. Let me just do the thing in the middle, so I don't have to think about it anymore. And then they pick, in this case, they would pick Infinity, the thing in the middle. Good on all that? The Ultra Clean 99 from Respicare works in a similar fashion to the Secure Air, where it's charging stuff. It doesn't do it quite as robustly, but it does in fact work fairly well. It's got these little ionizers that are charging things in the air and trying to get them to clump that way. They also have a little brother to that called the Micro Clean 95. Right, the Ultra Clean 99 is called Ultra Clean 99 because it's supposed to get 99% of the crap. The Micro Clean 95 is trying to catch 95% of the crap. It is a lower MERV rating, MERV 13 versus MERV 15, but it's MERV 13 with like a 1-inch filter. It does have electrical wires to it. Typically, these are mostly 24 volts, so low voltage electrical wires to charge up that grid. When you see the filter media, dude, like you can look right through it. It looks like what do we got going on here? Like it's like a piece of cheesecloth. It's like nothing, man. Because it is pretty much nothing. The filter media is low end, like super low end. But because the grid is charging all the stuff in the air, it's clumping it together. So the low end filter media can catch a bunch of stuff because everything's big. It doesn't ever see any small things. It only sees big things, and big things are easy to catch. Essentially, what's happening. All right, what kind of questions you guys got? Anything we discussed so far? Air quality in general, how a filter works, how a electronic filter works. Let me check this chat box thing. Okay, I think we're good on the chat box. If you have a question, type it in the chat box. I think you can also unmute yourself and just blurt things out. So do one of those two things as questions come up here. Next thing up is UV lights. UV lights have been around for decades and decades and decades. When I started here in the 90s, they were already decades old at that point, right? It's been around forever. Somebody did type something in the chat box. Enrique asks, just for the newbies, oh, my thing got in front of it. The high, like a little box pops. Okay, just for the newbies, the higher the MERV rating signifies what? The higher the MERV rating, the better it is at catching small stuff in the air. So a MERV 8 catches like decent sized things. A MERV 13 catches a bunch of tiny crap. And a MERV 15 catches really tiny crap. And then beyond that, we'd go to HEPA filters, which are off the MERV scale. Riley says, can you explain the differences between electronic and regular filters when you get a chance? Just trying to get a better understanding. So there's like basically there's three kinds of filters we would use, like say residentially. There's electronic filters, electronic air cleaners, which charges the stuff in the air. So there's electrical power going to it. When air comes through, it charges that stuff, let's say negative. Then as it moves a couple inches into the filter assembly, there's metal plates there, and those plates are charged positive. And negative things and positive things, opposites attract. I'm sure you've heard that. It's not just like a dating thing, like it comes from electrical. Negatives and positives attract to each other. So the particles in the air that are negative attract onto the plate, and that metal plate starts getting covered with dust and debris and crap. And every once in a while, every month, every 6 weeks or whatever, you turn power off, you pull the plates out as a homeowner, you wash the dang plates off, dry them, put them back in, and do it again. Because once the plates are full, that's it. It doesn't do anything anymore. And now you have no filter. That's like a normal electronic air cleaner. The regular filters are the media ones I explained before, the mechanical ones that are using impingement, straining, all that kind of stuff to trap the physical debris. In those cases, the dirtier filter, the better the filter is at filtering. So electronic filters catch less stuff over time until they're cleaned, and regular filters catch more stuff over time until they're swapped. But you can't let them go indefinitely because then they'll have no airflow through them. And then the third type was when we combined those two things. That was the Infinity, Evolution, Secure Air, Ultra Clean 99, Micro Clean 95, where I have electricity and filter working together as a team. So hopefully that helps a little bit more. Also, if anybody has joined a little bit late, I did record this, or I am recording this. At least I think I hit the record button correctly. So I can send you a link to it, like an hour afterwards. If you want that, just send me a note and I'll send you the link, and you can watch the first 15 minutes that you missed or whatever. All right. I'm going to keep moving on here. UV lights are the next thing up on the docket to talk about. So we've had UV lights for decades and decades. If you did not know, light travels in waves, right? So what that means is if you were examining the way light would work, just light, sound, all that kind of stuff travels in waves, right? And then the wavelength, the length of each individual wave, that distance, if you will, that length, is what we're talking about here. So that's in nanometers. You don't need to know that. It just is what it is. But we have all kinds of different light coming from the sun and any other sources of light. And UV light, ultraviolet light, these are the main versions we have: UVA, UVB, UVC, which we use a lot for IAQ stuff, and UVV is the other ones that we use for some stuff nowadays. And there's just the different wavelengths on there and then what you can do with that. So a lot of that stuff's coming from the sun. Some of it gets reflected back out by the atmosphere, by the ozone layer and stuff like that. Some of it makes its way through. UV light from the sun is very good at killing germs. Sunlight kills germs. Sunlight kills all cells pretty much equally. It's not discriminatory. So if you go outside and it's sunny, your arm will start getting sunburn on it. It's literally going to burn and kill the cells. Or maybe you do a really good job tanning. It's turning them brown. They're still dying, by the way. So the sunlight is killing your skin cells constantly, and then new skin is under it waiting to go. So it kills everything it shines on. The example I usually give people is, years ago, 20 plus years ago on our honeymoon, my wife and I did like one of those day catamaran trips on like an island kind of thing where they take you out on a boat and give you a bunch of rum and stuff, feed you lunch, and you hang out on the beach and then they take you back, right? That kind of thing. So we get there. I don't drink rum, by the way, because I had a bad experience back in college. That's the only thing they had on this boat. So I began drinking rum. So that's already the first problem, right? Now I drink rum because, that cured me that day because I had nothing else to drink. But then the guy that drives the boat is also the guy making lunch. He gets off the boat with his bowl of raw fish. He sets it down on a tree stump on the beach, squirts lime on it, and then starts walking away. And I was like, "Hey, bro, man, you can't just like leave the raw fish out here all day." He's like, "Yeah, we can." I'm like, "No, dude, we can't have raw fish sitting out in the sun. It'll go bad." He's like, "Dude, the sun is gonna make it nice. It's gonna be great. It's gonna kill all the germs." I was like, "I don't think that's the way it works, man." He's like, "Well, that's all we brought for lunch, so good luck, bro." And then that's what we had for lunch. So later on, being the nerd that I am, I go and research that, and the sunlight actually kills the germs on all the surface of the fish. It doesn't cook the inside of the fish. Can't get to that, but the outside it does, and the outside is the part that touched the knife, and hence the part that probably has germs on it. So between the lime juice having killing power and the sunlight having killing power, away we go. And now it's one of my favorite things to eat is raw fish with lime juice on it. And that sounds weird. In any case, sunlight's killing all that stuff, and it's been going on on purpose with mechanical systems for years. We've been putting UV lights in mechanical systems for decades and decades and decades. Since the 1950s, we've been doing that. So the UV light breaks down the DNA of the organisms that it shines on. In order to do that, you need two things. You need a high source of energy for the light. It can't be some like little wimpy light. It can't be a flashlight with an LED on it. It's got to be pretty intense light, and it needs to be shining on it for a long time. The amount of energy of the light bulb multiplied by the time is what is called the CT value, or what I call the kill dosage. How much of this thing do I need in order to kill various germs? There's actually a unit of measure for it. It's microwatt seconds per centimeter squared, which you do not need to memorize that for any reason. That's just a nerd fact for trivia that'll never happen in your life. All right, there's a unit of measure for how much microwatt seconds per centimeter squared of CT value kill dosage you need for each and every individual bacteria and virus. So the amount of energy source and the time. The amount of energy diminishes the further you get away from it, just like the sun. If I'm at the equator is the closest part to the sun, so it's pretty high intensity. Versus if I go up into Canada, it's not quite as intense. People in Canada or people vacationing in Canada don't usually come back with a sunburn. People that go down to the equator usually do. Right? It's more intense. You don't realize how fast it's burning your skin, right? Whereas in Canada, it takes longer. So the farther I get away, if I just say 1 inch away, if we call that 100% power of the bulb, if I get 2 inches away, I lost 75%. And if I get 8 inches away, I've lost 98% of the energy. So it kills way more germs over here than it does down here. It kills these, but they got to hang out longer for a longer period of time. So each known germ has a microwatt per centimeter squared kill dosage associated with it. This chart is showing you all the majors, and it's showing you how much energy I need to kill 90% of those germs and how much I need to kill 99% of those germs, which are obviously pretty good amounts, right? And then, so these are bacteria. Over on the side over here is mold, viruses, etc. So I made a couple examples, and this is the same examples I've been using for like a decade. So probably need new ones. But at the time, the best bulb I could find, the best UV bulb was 800 was the intensity of the bulb, measured at 1 foot away. That was the best one. Now you can get over 1,000, but at the time it was 800, right? And I knew the velocity of air moving through the filter, assembly, and air handler. Right? I picked a specific germ, in this case, Bacillus subtilis spores, whatever the heck that is. And I need 1,160 to kill 90% of those guys. So this thing right here. I need 1160 to kill 90% of those buggers. And then I also picked influenza, the flu, common virus, and I wanted to kill 99% of it, and I need 660. Well, if I know the intensity of the bulb, I know the kill dosage, I can do the math backwards to figure out the time. I need to shine on these bacteria for 14 and a half seconds in order to kill them. I need to shine on this virus for 8 seconds to kill it. Air moving through a duct isn't lingering out by the light bulb for 8 seconds. It's flipping through there really fast. So trying to kill germs in moving air is really hard, and you are not going to be able to do it with a UV light. I know that that probably contradicts most of the things that you've heard, um, especially for anyone selling you a UV light. But UV lights do not clean the air. They don't. I mean, they do, but they only clean the air of things that are right next to the bulb, like 1 inch away. And everything further away, it's not doing anything for there. Now, if I was a UV bulb salesman, I'd be like, well, yeah, Ryan, but like, let's say I get 1 second of shine time on that bacteria. Then the bacteria goes around through the house and back through the return duct, and it comes back again for a second pop. I hit him again. And after 14 and a half times around, I got him. I killed him. It's a cumulative thing. Don't you understand, Ryan? Yeah, I get it. It is a cumulative thing. Just like if I go out in the sun for an hour and I walk under a tree for 10 seconds, the clock doesn't restart on my skin dying. I'm already an hour in. So I walk back out from the tree and now I'm at 1 hour and 1 minute, right? Clock keeps going. I get it. But the chance of me getting that virus to come back or that bacteria to come back 8, 10, 14 times, probably not making it back into the airflow that many times. So UV lights are absolutely useless for killing germs in the air. Absolutely useless. Our industry sells a lot of them for that reason, and they do nothing for people, literally nothing, in terms of killing germs in the air. You also have to put them all over the place. This one was even smart. They put them this direction. So that way the germ has to pass by it all the way through. But even still, so instead of, whatever, 0.08 seconds, it's there for 0.12 seconds. It's still not enough to do anything. It's still pretty useless. So what the hell are UV lights good for? UV lights are good for cleaning coils. They're really, really good at cleaning the evaporator coil because the evaporator coil is not moving. I don't care if it takes me an hour. I don't care if it takes me 10 hours to clean the coil. It's fine. I got all day. Let the light shine on the coil all the time, constantly. The air is moving. It's hard to kill germs in the air. But on stationary stuff, specifically the evaporator coil and the condensate pan, they're not going anywhere. They're there all day long. This is a real coil example. This coil started out looking like this guy. And just by shining the light on it, it looks like this guy. Now, we don't tell people to do that. We tell contractors clean the coil manually, like chemically clean the coil, and then put the UV light on there to keep it clean so the bad stuff doesn't grow back. But if you wanted to, you could just shine it on there and let it kill everything. The problem is it takes a while, so there's still germs floating around, right? Plus all this crap flakes off and it clogs up the drain pan, which no one wants. So clean it manually. The UV light keeps it clean after that. In addition to killing germs on the coil, and those are the germs that could later flake off and end up in your air and cause you health problems, it also keeps things pretty good from an airflow standpoint. When germs and stuff grow in the coil, it blocks off the airflow. These are just different pictures of that, right? So I'd rather have, this is the same coil, by the way. It starts off fairly clogged because it was in pretty bad shape. And it ends up after 3 months, it's got pretty good gaps where I can get airflow through there. Obviously, it's better to clean it off manually and use the UV light to keep it clean, but it does a pretty good job. Questions on UV lights? Coil cleaning. Excellent application for coil cleaning. If people have crap growing on their coils, A, that shouldn't be happening. There's other problems going on, but a UV light will solve that particular problem. We also use UV lights for other stuff, but not for UV light applications. So specifically, we stick them in some of these air cleaning products Typically, they're called PCO, photocatalytic oxidation. I'm showing you a bunch of ones from Respicare here. There are other suppliers that we have had historically over time, but the ones we use the most of are Respicare based. So photocatalytic oxidation, photo means there's going to be light involved, i.e. the UV light bulb is what I'm using to generate that, right? And then catalytic, it's a catalyst reaction, and oxidizers are what's created. Oxidizers have the killing power. If you ever bought like laundry detergent that's like tied with oxy, the oxy is what's killing extra stuff in there, right? So this is the same idea. For a brief while, I had photocatalytic oxidation water cleaning for my washing machine. We had a device we were beta testing for GTI. They since took it back. But it was awesome. We had like a whole entire year, 12 months, no laundry detergent at my house. None. This device just it cleaned the water. It oxidized the water. Not only cleaned the water, it turned the water into a cleaning ingredient as it came into the washing machine. So it's like the detergent was being put into the water via a light bulb as it passed in there. It was awesome. They ended up going forward doing the technology, but it's only available for like large laundromats, not for houses. But it was awesome when we had it. You can do a lot of cleaning power with oxidizers. So if we have one of these PCO devices, first off, it has a UV light in it. So if it does happen to be near the coil and the light is shining on the coil, great. It helps clean the coil. That's like a bonus to this thing. The other part is sometimes they have carbon cartridges. Not always, but sometimes they do. Carbon are the black cartridges on the side. So this one on the picture has carbon on the side, and then it has titanium on top. But the black ones are carbon. They're really good at absorbing odor. So if your problem in the building is more odor related and less germ related, you might want to choose one of these types. But usually we're picking ones that are all white, all titanium. That's the PCO side of the equation, photocatalytic oxidation. So the little white plates, they have titanium dioxide embedded into the plates. When UV light shines on titanium dioxide, it creates anywhere from 3 to 4 oxidizers that then get shoved down into the air and start attacking stuff in the space. Specifically, it creates oxidizers that are hydroxyl radicals. I know you were not coming here today for a chemistry lesson, but radical means it's unstable, and radical things in the environment want to join up with other things to become stable again. So we're intentionally sending stuff out into the air that's completely unstable for it to grab onto the other stuff in the air and turn it into a different chemical. And hydroxyl means hydrogen and oxygen. So we're sending various forms of hydrogen and oxygen in weird combinations that don't normally go together in order to get them to rip other things apart. So an example of that would be UV light bulb shines on the titanium dioxide plate. It creates 3 or 4 oxidizers. This is just one of those oxidizers. O meaning oxygen, H meaning hydrogen, and it happens to be charged on it. So, positively or negatively charged. Those things go out into the space. They rip apart other chemicals, or they also, because of the charge associated with them, they'll clump around stuff like germs and isolate that germ from the rest of the air, and hence it won't be able to get the hydrogen that the germ needs to survive. Most of them, those PCO devices, are doing these 3 oxidizers, not that you need to know what chemicals they are. Some of them are also creating a fourth oxidizer, which is O3, also known as ozone. That's the fourth one. So specifically the Oxy 4 from Respicare, Oxy 4 meaning 4 oxidizers, creates all 4 of these. Ozone is the most powerful of the 4. It kills the most germs. However, ozone in higher dosages is not good for you. So many people don't want it, even though this one's in a low dosage and it's safe. People hear the word ozone and they're like, I'm out. And they don't want that. So you can get the Respicare device without the ozone oxidizer, although it's not going to do as good of a job. The the one with the Oxy 4 one has a UVV light bulb, and the other one has a UVC light bulb. That is the difference between them. And that the UVV creates a different extra fourth oxidizer. Obviously, they have all the coronavirus testing. They have testing on everything. I'm not going to go through it. I'm not here to pitch the product to you. I'm sure you're already familiar with it a little bit. You probably have even had uh, I forget the lady's name from Respicare. Andrea come in and talk to you guys about it at the store. But they do a good job publishing all their data and whatever lab it was that tested it and telling you how many hours it takes to kill various kinds of germs in people's buildings and stuff, right? And it's all different kinds of labs, universities, and whatnot, right? To Concordia University, like whatever the test facilities are. So I'll skip that in the interest of time to keep you going. I will mention, because you may have to help people at the counter with this, um, I used to have at my house probably 12 years ago now, I put in a PCO type device from RGF, which we used to sell at TEC. I put that in after much pressure from other people to try it. I was very skeptical. At the time, I had two small kids. They were both in preschool. They would go to preschool. One of them got sick of preschool, and everybody gets sick of preschool because it's like a giant freaking petri dish of germs. Like she would come home and she'd get her little brother sick, or vice versa, right? And they'd always get each other sick. The day we put that device in was the last time anyone in my house has ever gotten sick from anybody else. We went 3 straight years of no one getting sick from anybody else. And then finally, one of my kids got the other one sick. My wife's like, I think your little bug zapper isn't working. That's what she calls these things, right? I'm like, it's not a bug zapper. And I started explaining technology. She's like, I don't want to hear your nerd explanation. I'm just telling you your other kid got sick, man. So I'm like, there's no way. They're like, that thing's been cranking for the 3 years. And I was like, oh crap, it was a 3-year bulb. I go down there, the bulb was burnt out, right? Put a new one in, boom, another 3 years, nobody getting sick. And at that point, I had 4 kids. So basically 6 straight years, other than the time the bulb died, of no one getting sick from anybody else in the whole house, which I thought was awesome. So I became like a Kool-Aid drinker on this. So we switched to Respicare as a company at TEC instead of the RGF because the RGF was A, selling to train. We don't like that. And B, selling direct to homeowners. We definitely don't like that. So we switched over to Respicare, which had similar competing technologies. I didn't want to switch because I'm like, I got a good trend going with RGF. I'm just going to keep using that. And they're like, well, we don't sell that here anymore. I'm like, that's fine. I'll go to Bruckheimer and buy the bulb. Like, I'm good with that. I'm like, no, you got to put this in. And finally, somebody at TEC talked me into it. The magic words were, we'll give you one for free to try. That's what the lady from Respicare said. I'm like, all right, free. I'll try free. I'll risk my children's health for free. I put it in. Dude, this thing did not work. My kids were sick almost immediately off of each other. First time one of them got sick, they all got sick. So I'm like calling her up. I'm complaining to her. She's like, well, maybe you had a bad one. Let me send you a new one. Fine, send me a new one. Sends me a new one. Also doesn't work. So I'm less excited. Then she's like, well, maybe your family's just dirty. I'm like, okay, that's nice. She's like, no, I don't mean it mean like, but I'm just saying like maybe you got a lot going on. Maybe you need the high output one. So instead of the 7-inch one, she sends me the 16-inch one. I'm like, fine, the commercial grade one. Threw it in, still no good results. So at this point, I'm mad. I'm like literally mad at her. I'm like, I'm gonna go back to getting the other thing. She's like, well, you rotated the clips, right? I'm like, what the hell are you talking about? What clips? It's like in the manual on page 6 or whatever it was, you got to rotate the clips if you want more output. I'm like, no, I didn't rotate any clips. I didn't read the manual. You think I'm reading the manual? I shoved it in a hole in the duct and I plugged it in. I didn't read anything. She's like, yeah, you got to rotate the clips and you get more output. We ship it to you with 75% of the bulb blocked off with these metal clips and only 25% is doing anything. I'm like, why the hell would you do that? It's like, well, some people don't like the maximum output because they can smell it and they get annoyed by it. So we ship it that way. And if you want more, you just rotate them. I'm like, what the hell? So you rotate them, you get 50%? She's like, yeah. I'm like, what if I take them off? She's like, well, then you get 100%. So I took them off. Dude, I'm like 6 years into it now with no clips on there. And I've, upgraded my bulb since then. It's been great. It's been awesome. So I'm mentioning it to you so that you understand when people at the counter are asking you questions about the damn clips. This is what the hell they're talking about. Those clips can be rotated or they can be completely removed. Respiracare has all kinds of stuff other than the air filters we talked about and the UV lights that we talked about and the Oxy 4s and all those kinds of devices. They have all kinds of versions of that. But for the most part, Oxy 4 and MicroClean 95 are the two most useful things in my opinion. All right, let's see if we can squeeze one more technology in for you. Bipolar ionization. So bipolar means two, bi, right? So bipolar means two ionizers. There's one, there's two. So we started using these devices. You guys probably know we use GPS as a product we sell here. This is the second time we've had them. The first time we had them way before COVID, like 8 years before COVID, we were doing it mainly for commercial air handlers and we would occasionally do it for small residential. Some of our dealers liked it because they didn't like the bulb solutions because the bulbs had to be replaced. I don't understand why they wouldn't like that. You would think putting a new bulb in for people every year or every other year would be a good sales revenue for them. But some of them are like, I don't want to sell people something. They gotta keep maintaining it. Okay. So these started getting used residentially because there's no maintenance involved. Like you basically, the only maintenance technically is that once a year with an alcohol wipe, you just swab it off, and 10 seconds later, you're done. That's like your maintenance. Like if anyone even does that. So anyway, it's bipolar ionizers. So basically, this one is charging everything in the air negative. This one is charging everything in the air positive. Those things collide together. They clump together. They become bigger, more likely to get caught in filters, more likely to fall down and get vacuumed off your floor in the kitchen, et cetera, et cetera. Similar to the technology you mentioned before, but this one is just stuck in as a retrofit, not part of an actual filtering system, just shoved into the blower section on its own, if you will. It's natural. Ionization is natural. It's like the other stuff. The oxidation was also natural. We're obviously forcing it to happen unnaturally, but it does occur in nature, generally through falling water, waterfalls, rain, etc. So same kind of stuff we talked about before. It's creating these unstable radical type things that are hydrogen and oxygen based, and they're going through and ripping things apart. An example might be if I have ammonia in the air, which is a cleaning chemical, right? You can clean counters and stuff like that with it. It is 3 parts hydrogen, 1 part nitrogen. Hydrogen's not bad for you. Nitrogen's not bad for you. But for whatever reason, you clump them together in 3 hydrogens, 1 nitrogen, it's bad for you to breathe. When it goes through this plasma field generated by the ionization, that breaks them apart into 4 individual things. They could regroup as ammonia, but ammonia is fairly complex, so that's unlikely. It's more likely the hydrogens jump on an oxygen atom, 2 hydrogens and 1 oxygen, that's H2O. That's fine. I got 2 nitrogens double up together, that's N2. That's the nitrogen you have in the air. 78% of our atmosphere is made of nitrogen, right? N2. So it took something that was fairly dangerous and it regrouped them into non-dangerous things. And the byproduct being nitrogen and water, not a problem at all. It also, because it has the positive negative charging, it does clump around various germs and it basically starves them off. So that's the hydroxyls, the hydrogen oxygen radical things we talked about before, and it deprives them of the hydrogen they individually need to survive. You need oxygen to breathe. They essentially breathe hydrogen and they can't get it. You can combine these things. If we take a pretty good MERV filter, let's say a MERV, where'd my mouse go? What the heck, dude? All right, there we go. Let's say we take a MERV 10 filter. It will catch 12% of, in this case, SARS virus. By the way, this test is before you heard of COVID. This is, I think it was the 7th SARS virus we had. COVID-19 was caused by SARS-CoV-2, which was the 7th well-studied virus that we had. Like this goes on all the time. There's probably a new one right now. We don't know anything about it. Anyway, so this testing's been going on for a long time too. It takes this MERV, in this case, takes that MERV 10 filter. It catches 12% of those. I combine that with a UV light. The filter and UV light catch or kill 35%. Instead of a UV light, I combine it with an ionizer. Now we catch or kill 89%. And if I go even higher, like say I put in a MERV 15 filter, like an infinity air purifier, all right, I combine it with an ionizer, I'm up to 99%. It's pretty good clip. So you can make low-end filters do a better job. In this case, once I'm past this line, I'm already doing a pretty good job, like in general. But MERV 10, 11, 12, 13, 14 filters can receive a pretty good enhancement from these other accessories being put on there. And there's lots of studies to support that. We do GPS again during COVID. The GPS rep sucked so bad. I don't know how you couldn't sell GPS during COVID, but I'm not involved in sales, so I don't know how that works. But they sucked so bad that GPS asked if we wanted to get re-engaged with it, which someone in their office said yes. So we started doing it, in this case, more for a residential, small commercial, and less for big, hospital air handlers. But they have all kinds of different technologies. Some of the ones we use now actually have these little wiper blades on them, if you will, that, like a windshield wiper, wipe the little thing off. Like once a day, a little motor turns it and wipes the debris off. So you don't even have to bother cleaning it with an alcohol wipe every once in a while. You don't have to do anything. So they have all these. They're based on the size of the system. There's all kinds of different configurations of them, which we're not going to dive into today. There's even ones that fit inside ductless mini splits, hotel PTAC units, really tight compressed areas, large commercial ducts, small residential ducts, et cetera, et cetera. There's all kinds of locations you can shove these things in. All right, I think we're doing pretty good there. I'll mention a couple last things. I realize we're over the hour. If you have to go, I totally get it. If you want to hang out for 5 more minutes, I'm going to finish these off so that way you have all the info. Carbon monoxide alarms are required whenever there's combustion appliances like a furnace or a boiler. We historically have sold these. It's not very exciting when we sell them because they just plug in. There's nothing any more exciting than you could buy at Home Depot as a homeowner, but nonetheless, we have sold them historically with little carrier logos and stuff on there. But anytime there's a furnace, people need to have a carbon monoxide alarm there. We also sell duct smoke detectors. This is primarily used for commercial applications. Whenever you are above 2,000 CFM, so basically more than 5 tons of cooling, you are required by code, pretty much everywhere we do business, at least one code, if not two codes, require this, to have a duct-mounted smoke detector. And whenever there's smoke in the duct, it disables the fan system. Because there's no reason to have the fan suck smoke out of one portion of the building and distribute it to all the other areas of the building. That's stupid. So that's what those do. You can use these residentially. People don't typically do that, but you can in fact do that. Duct sealing helps out with air quality. We'll talk about that real quick. Obviously, dehumidifying the air removes mold, which is helpful for an air quality standpoint. And believe it or not, humidifying it helps as well. When air is really dry, certain viruses and bacteria really thrive, which is why when November, December comes around, we call it like flu season because things start getting dry and the flu does really well when it's dry, and as do other germs. And then you can always bring in fresh air from the outdoors to help make things better because almost everywhere in the country, the outdoor air is much cleaner than the indoor air. Indoor air is the worst. So we get fresh air from outside to dilute down the polluted indoor air. Duct sealing, we do it with AeroSeal at our office. We have several dealers that we at TEC work with to do this. Um, Essentially, what happens is on a temporary basis, we cap off all of their registers in the building, in the house. We close them off, and we suck air into a fan box, and then there's a nozzle on there that injects an aerosol. Think of it as someone standing in the tube holding a can of Aquanet hairspray, just spraying away, like just cranking on it. It's not technically Aquanet hairspray, right? But that kind of idea, something sticky and tacky, and it blows it into the tube, into the duct, and then if there's a leak in the duct, it comes out the hole. Obviously, it can't go out the duct because the duct's blocked off, so it leaks out the hole. As it leaks out the hole, it scabs the hole closed. It basically it's aerosol based glue. So the glue scabs the hole closed, and then that hole is no longer a hole. It's a gooey gummy scab essentially. So you can seal the ductwork up pretty well that way. I'll skip the humidifier discussion because I'm sure you've all been on 75 April Air webinars and know how a humidifier works in general. The one thing I will, in fact, say about humidifiers is that modern homes do not need them. If your house is 20 years old or less, you probably don't need a humidifier. I also say that from personal experience. My house was built in 2002. I put a humidifier in it in 2003 when we were doing stuff, and it never ran. Like never, ever, ever, ever ran. I think my house has never been below like 33% humidity, something like that. If you get enough kids running around sweating and the house is tight, it's not a problem. When you look at April Air or Honeywell stuff, they'll always have a chart like this that says, hey, if you have this square footage or this cubic feet, you need this amount of gallons per day of humidification. So let's just say I have 20,000 cubic feet of space. I have to decide if my house is tight, average, or loose. If I just say, well, average, because I don't know what these numbers mean, so I just pick the middle because I'm lazy, I need 14 gallons per day. And I would get a humidifier based on that. What they do not tell you is what tight, average, and loose mean. They don't define it for you in these charts. They ignore it. If you have a newer construction home the past 20 years, you are tighter than tight. You're up here somewhere. Tight house. This chart's from like 1960, dude. Tight is basically a loose house today. So you're over in the like, I need like 1 or 2 gallons a day category. You'll accidentally get that by running your dang shower. So newer constructions homes built in the 2000s, for the most part, don't need a humidifier. And if they do, it's because the house was not actually built to code. It was built crappy, and hence it leaks and dry air is getting in from the outdoors or moisture is getting out from the inside out. So tighter the house is, less you need the humidifier. With that being said, the house I grew up in, built in 1956, I think it was, man, I wish we had a humidifier. It was always so dry in there. Older houses for sure need humidifiers, right? New tight houses do not need them. And then the last thing is there are ERVs. That's like a whole nother discussion. If you want a lot of info on that, I have an entire recorded like video series I can send you the links for. I can explain how that works. But essentially, what happens with an ERV, the quick example of an ERV is that it removes air from your home and exhausts it away, and it sucks fresh air in your home. And in between those is a heat exchanger. And that guy is taking heat and absorbing it. Let's say it's wintertime. It absorbs heat from the air you're exhausting and it transfers that heat to preheat the outside air coming in. So the air molecules don't mix, but one airstream heats the other airstream. So essentially what you do is you duct your bathroom exhaust fans and things like that to be exiting out, which you got to duct them out anyway. But instead of ducting it out to go right there, you duct it to go out the ERV, and then the fresh air comes in and takes its place. So if you need more help on that, there's a whole longer version of that I can spend time with you guys on. All right. Any last pending questions before we break up for the day? I went 16 minutes over, I think, which is pretty standard. I don't know if I've ever been on time. I'm gonna leave it open for like a minute or two and see if anything else pops up that I can try to answer. All right, I don't see anybody typing anything in, so I'm gonna go ahead and end the webinar. And if there's other topics that you guys would like to learn about in the future, please let Rob Kenny or myself know, and we'll figure out who at TEC has that expertise, and we'll try to get that in front of you one way or the other. Thank you guys for your time.